Hi everybody. Today we are finishing up Chapter 2 in Mechanics of Materials. We're going to just cover a few odds and ends. One is called Saint-Venant's principle. The next are how to handle stress concentrations. And the last is the definition of an elastoplastic material. So first, let's start talking about Saint-Venant's principle. The diagrams here show a structural member, some sort of a net indicating the layers and columns of the structural material. And as you can see, when you push, and this happens with pulling as well, that in the vicinity of the application of the load, that there's more deformation and more stress really than in other parts of the material. So what Saint-Venant's principle tells us that if we move a certain distance from the application of the load, and specifically if we compare that to the width of the item. So if the structural member is B wide, if we go down B amount from the point of application of the load, that we will not really have a large variation in the regional stress. So in other words, sigma average, after you get past this distance B from the point of application, sigma average will be a pretty good representation of the stress. And you can see the numbers down here, that the minimum stress would be 97.3% of the average, and the maximum would be just 1.027 times. So basically 2.7% more. So in other words, that stress profile is pretty flat. Now, when you're only half of that distance, you see that the stress profile becomes more pronounced, and that the minimum is 66.8% of the average, and the maximum is almost 1.4 times as much, or 40% more. And when you're only a quarter of the distance wide, if you're that close to the point of application, the minimum is only 20% of the average, and the maximum is 2.6 times as much. So what this means is, if we are looking at a point of application as far as design, we really cannot talk about P over A as being a good value for the sigma that we would design for. We would have to increase that quite a bit. So this is basically Saint-Venant's principle, is that the stress distribution may be assumed independent of the mode of load application, except in the immediate vicinity of the load. So if you're in the immediate vicinity of the load, you have to design for a higher stress. Now, in your textbook, you'll notice that when they have problems like this, they will often put a rigid end cap or some sort of a plate on the end of the structural member. And that's sort of their code for distributing the load in the vicinity of the point of application. All right, so Saint-Venant's principle starts us into this conversation about stress concentration. Anytime that you have a discontinuity in a structural member, the stress will concentrate somewhere in the vicinity of that discontinuity, generally speaking. And there are a lot of different discontinuities, but in this chapter of this textbook, we're only going to talk about two. We're going to talk about a flat bar with a centric hole in it. What we're going to talk about is a flat bar with a fillet. Okay? Now you can kind of think about here, for example, why would there be more stress than if you just calculated P over A? Well, for one reason, here in the vicinity of the hole, the area is quite a bit smaller, isn't it? In other words, when you pull on this flat bar with a hole in it, right through the middle, there is less area to take up that stress, or that the stress is going to be directed differently because of the radius of that hole. So this diagram just shows you a little bit about how that works. Now, the way that we handle it, or the analysis technique, is to use a graph. And I want to assure you that in our book, all we're going to use are flat bars with holes, flat bars with fillets. If you were designing for a different configuration, you would have to have specific information for that configuration. So it's not like you have to worry that we're going to encounter problems with, two holes or a not flat bar or something with a fillet on one side and a flat edge on the other. So this is just to give you an example of how stress concentrates and how we deal with it as engineers. So the first thing is that we want to find this concentration value K, because K is equal to, it's a dimensionless constant, it's equal to sigma max over sigma av. Now you know that sigma average is just P over A. So what this means is if we can find the stress concentration factor, we just multiply it by sigma A to find sigma max, which is the sigma that we actually need to design for. So in a flat bar with a fillet, you find on the x-axis or the horizontal axis the factor R over D. Well, what is that? R is the radius of the circle that's cut in the flat bar, and D, you'll notice, is small d, not capital D. D is actually the distance that is not taken up by the circle. So in other words, it's capital D, which is the width of the bar minus the 2 times the radius of the circle. Or you could say the width of the bar minus the diameter of the circle is equal to D. If you measure from the top of the circle to the edge of the bar, that's 1/2 D. So in other words, it's the area that actually exists in the vicinity of the circle, or the length of bar that actually exists through the center of the circle. So anyway, so we find R over D, and then say it was 0.3. We just find that value on the horizontal axis. We go up to where our vertical line intersects this line, and then we come over to the left-hand axis, the vertical axis, and read K. So in the example I just gave, if R over D was equal to 0.3, K would be almost 2.4. Now you can't really read this graph very carefully because the gradations are not very fine. But you just need to show me your process, and I'm not expecting you to carry this out to several decimal places, as that would be impossible. Anyway, you find K, calculate sigma average, and then you are able to calculate sigma max. Now, if we have, on the other hand, a flat bar with a fillet, we have a little bit different geometry, and we have 2 factors that we need to find. But basically, little r is the radius of the fillet, little d is the width of the neck of the bar, and capital D is the width of the body of the bar. So the first thing is we calculate the ratio r over little d, in other words, the radius of the fillet over the width of the neck. Then we have another factor to compute, which is the width of the body divided by the width of the neck, or capital D over D. And we go in at r over little d, so say that was 0.10. We come up to a different curve. In other words, on the flat bar with a hole, there's only one curve. On a flat bar with a fillet, there are many curves. So perhaps d over d is equal to, say, 1.5. So we would come up to this line, and then we would read over to the left-hand side and find a K value of just over 2.2. And at that point, we use K in the same way as we did on the flat bar with the hole. We multiply it by sigma average in order to get sigma max. Okay, so those are the only 2 shapes that we're going to study in here, but rest assured that there will be many other shapes that you would have access to, but for this class, this is giving you a taste of how that works and just a smidgen of the analysis that is required of you if you have either a flat bar with a hole or a flat bar with a fillet. And here's just an example, and you can see this. We're asking for the largest load, which we know is P over A. Okay, and we find we have some information, and then we can find the normal stress that is allowable, or the maximum, and then design for that. And there's just our data. So we calculate that ratio, D over D, 1.5 R over D, which is 0.2. So we come in here at 0.2, and come up to 1.5, and then we read over to left, and I get a value of just over 1.8. They define it as 1.82. Then we put that on the bottom with the sigma max and find sigma average. And in this case, we know that sigma is equal to P over A. So if we multiply sigma average times the cross-sectional area, we find the P, or the load that we can apply in order to not exceed our limits on this particular bar with a fillet. All right, now the last thing I wanted to talk about is it's an idea. It's not a real material, but it's called an elastoplastic material. Now we had talked about this graph earlier where we have a sigma and an epsilon. So we're talking about a stress versus strain diagram. From point A to point B on this diagram is the elastic region, and then beyond that are some permanent sets, some residual stresses, and but basically after we yield, the equations that we've talked about are no longer valid because the relationship between sigma and epsilon is no longer a linear relationship. But as we've discussed before, different materials behave differently after they reach B, after they yield or reach an ultimate or rupture, depending on the nature of the material. But a theoretical type of an analysis that is sometimes used in the analysis of plastic deformations is this idealized material, which is called elastoplastic. Now what an elastoplastic material does is it proceeds from zero stress strain, 0, 0 on the stress strain diagram, up to this sigma yield in a straight line fashion, so that once again here A to Y is the elastic region of behavior. But then instead of breaking or yielding, an elastoplastic, this idealized material, will just stretch to some longer, in this case, position without any increase of stress at all, and then it will rupture. So a straight line on a slope followed by a straight horizontal line concluding in rupture is the definition of elastoplastic material. Now there is no material that is truly elastoplastic, but an approximation to elastoplastic is used for design. So this is a term and an idea that you should be familiar with. All right, everybody, well, that's it for lecture 15, and that's it for chapter 2. I'll post the final homework problems, and you'll be ready to get started on Monday. We will come back and start with chapter 3. The homework for chapter 2 will be due Wednesday, so if you have any questions, make sure to ask on Monday. See you then.